pseudo metric, and some related concepts like closure, closeness, interior, exterior, frontier, and so on. So first of all, we start with one example. Suppose we are given a metric space xt and a real valued function d star, which is defined as d star xy equal to minimum of 1 dxy. Here dxy denote the distance between the points x and y for every xy belonging to x. Then this d star is a bounded metric on x. So to prove that d star is a bounded metric on x, first of all we will prove that d star is a metric, then we will show that d star is bounded. To check that d star is a metric, we will check all the conditions of a metric space. So first one is, we know that 1 is greater than 0 and dxy is greater than or equal to 0 because d is a metric on x. It means minimum of 1 and dxy is greater than or equal to 0, and it means d star xy is greater than or equal to 0. So first condition is satisfied. For the second condition, we see that d star xy is equal to 0 if and only if this minimum of 1 and dxy is greater than or equal to 0. But 1 cannot be 0. It means dxy means distance of x from y is 0, and this is possible only if x equal to y, because d is a metric on x. It means d star xy equal to 0 if and only if x equal to y. So second condition is also satisfied. Now we will check the symmetry. D star xy is equal to minimum of 1 and dxy, and this can be written as minimum of 1 distance between y from x, because d is a metric, so distance of x from y is same as distance of y from x, and this is nothing but, by this definition, d star yx. It means d star xy is equal to d star yx, means d star is a symmetric function. Now we will check the triangle inequality. Means we will show that d star xy is less than or equal to d star xz plus d star zy for all x, y, z belonging to x. So from the definition we see that d star xy is 1 if 1 is less than dxy, and d star xy is equal to dxy if dxy is less than 1. So d star xy is the minimum of 1 and dxy. So to prove the triangle inequality, we assume that this dxz is less than 1 and dzy is less than 1. Means this is minimum between 1 and dxz, and this is minimum between dzy and 1. It means d star xz is equal to dxz and d star zy equal to dzy for this particular case. So now d star xy is less than or equal to dxy, and by triangle inequality, because d is a metric, this is less than or equal to dxz plus dzy, but dxz is nothing but d star xz and dzy is nothing but d star zy. It means d star xy is less than or equal to d star xz plus d star zy. This was the case when this dxz is less than 1 and dzy is less than 1. Now we assume that dxz is greater than 1. It means d star xy is less than or equal to 1 because it is minimum of the two, or it is less than or equal to 1 plus dzy because dxz is greater than 1. So this is equal to d star xz, because d star xz is 1 in this case, and dzy is d star zy. So in this case also d star xy is less than or equal to d star xz plus d star zy. So similarly, if we assume dzy to be greater than 1 and proceeding like this, we can show that d star xy is less than d star xz plus d star zy. It means all the conditions of a metric are satisfied. It means d star is a metric on a set X. Now we will show that d star is bounded. It is obvious that d star is a bounded metric on X because X is a subset of a ball centered at X and radius R with respect to metric d star. And this is equal to the set of all the points x dash belonging to X such that this distance of x dash from X is less than R with respect to the metric d star for any x belonging to X. Here we should have close bracket, and it is clear that d star x dash x means distance of x dash from X with respect to metric d star is always less than or equal to 1 because by the definition of this metric d star. So it means d star is a bounded metric on X. We have proved that it satisfied all the condition of a metric as well as it is contained in a ball centered at X and radius R, so it is bounded. Now the definition of a pseudo metric. The pseudo metric space is a set together with a non-negative real valued function d called the pseudo metric such that for every x, y, z belonging to X, distance of x from y is 0, then x is equal to y, and distance of x from y is equal to distance of y from X, and distance of x from z is less than or equal to also dxy plus dz dy z, distance of x from y plus distance of y from z. Here it is less than or equal to. So the difference between pseudo metric and metric is that unlike metric space, points in pseudo metric space need not be distinguishable. Means in pseudo metric space we can have dxy distance of x from y to be 0 for distinct values of x and y. Even if x and y are not equal, even then distance of x from y equal to 0. In mathematics, pseudo-metric is a generalization of a metric space in which the distance between two distinct points can be 0, and it was introduced in 1934. One example of pseudo-metric is that if we consider two-dimensional real space and consider the function d to be to the non-negative real numbers by distance of x1 x2 to distance of y1 y2 equal to modulus of x1 y1 x1 minus y1. Because it is a two-dimensional space, so we have considered it to be ordered pairs, and we have defined a metric like this, that distance of ordered pair x1 x2 to y1 y2 is equal to modulus of x1 minus y1. Clearly, distance of x from X is equal to distance of x1 minus x1 equal to 0, and distance of x from y is x1 minus y1 modulus of x1 minus y1, and modulus of x1 minus y1 can be written as y1 minus x1, and this is equal to distance of y from X. Here x means x1 x2. Here x means x1 x2 and y means y1 y2. Because we have considered two-dimensional real space, so in place of x we have x1 x2, in place of y we have y1 y2, and we have defined it to be x1 minus modulus of x1 minus y1. So these two conditions are satisfied. The triangle inequality also follows from the triangle inequality on R1 because distance of x from y is less than or equal to distance of x from z plus distance of z from y, because modulus of x minus y is less than or equal to modulus of x minus z plus modulus of z minus y. So xt satisfies the defining condition of pseudo metric space. So it means this is D is a pseudo metric which we have defined like this. However, this is not an example of metric space, because if we consider any 2 points 2, 3 and 2, 5, 2, 3 is a ordered pair and 2, 5 is also ordered pair in two-dimensional real space, then the distance between the ordered pair 2, 3 and 2, 5 is, by this definition, 2 minus 2, because it is x1 minus y1. So 2 minus 2 equal to 0. So we have two distinct points, one is 2, 3, another is 2, 5, but the distance between them is 0. So this is the example of a pseudo metric, but this is not an example of a metric space. So we can say that every metric space is a pseudo metric space, but every pseudo metric space cannot be a metric space. Any pseudo metric space does not satisfy the properties of a metric space, because in pseudo metric space we can have two distinct points that are at a distance 0 from each other. Now the definition of closed set. A subset f of x of a metric space is said to be closed if its complement is open. This is a figure. This is a closed set inside it. For example, if we consider A equal to 0, 1, closed interval 0, 1, and B to be semi-closed or semi-open interval 3 to 4, in the set of real numbers, then we claim that A is closed but B is not closed. A is closed interval, see, this is 0 to 1. It is closed at 1 and closed at 0. And B is equal to closed at 3 but not closed at 4. Here we have this is this point, we have left this point. So we claim that this A is closed, which is from 0 to 1, and this is not closed. Suppose x does not belong to A. If x does not belong to A is from 0 to 1, it means either x lies from on this side or x lies on this side. It means x is less than 0 or x is greater than 1. Suppose r is equal to modulus of x, or r is equal to x minus 1. It means open interval x minus r to x plus r is a subset of A complement. A complement is this side and this side, because A is the point 0 to 1. But this is an open interval in A dash. It means A dash is open. This is not there. It means A dash is open. Or we can say that A is closed, because by definition a set is closed if its complement is open. Now let us consider a set B. The point x equal to 4 does not belong to B, but any open ball centered at 4 is of the form 4 minus epsilon to 4 plus epsilon, which does not intersect B. Hence the complement R minus B is not open, hence B is not closed. Now closure. The closure of A is denoted by A bar, and it is the intersection of all closed sets containing A. And we can say that a point is in the closure if and only if any open ball around it intersect the set. It means X belongs to A bar, means closure of A, if and only if there exists R greater than 0 such that open ball centered at X and radius R intersection A is not equal to 5. So a point is in the closure if and only if any open ball around it intersects the set A. Now we will prove that in a metric space, every closed sphere is a closed set. Suppose we consider a closed sphere centered at X and radius R, which we have denoted by S, and radius R as it is a closed bracket. It should be closed bracket here. SXR is equal to set of all the points A such that distance of A from X is less than or equal to R. So this is the definition of closed sphere. In case of open sphere, we have only less than sign here. In case of closed sphere, we have less than or equal to sign here. If Y belongs to complement of this sphere, then distance of Y from X is greater than R. Because we know that inside the open sphere, this closed sphere, the closed sphere is the set of all the points A such that distance of A from X is less than or equal to R. So if Y belongs to its complement, it means distance of Y from X is greater than R. If distance of Y from X is R plus 2 epsilon, this we have taken by choice, then the sphere N, which is centered at Y and radius epsilon, belongs to this complement of closed sphere, which is we have denoted by S dash XR. Since every point of N of this sphere Y centered at Y and radius epsilon is at a distance greater than R plus epsilon from X. It means this sphere S dash XR is the union of family of open spheres NY epsilon, of spheres like NY epsilon, and because it is a union of family of open sphere, so it is open. If this sphere is open, this is the complement of closed sphere SXR. So because it is open, so it means SXR is closed. Here it should be closed bracket. It is a closed bracket. To distinguish between open sphere and closed sphere, we write separate brackets. For closed sphere, we write closed brackets, and for open sphere, we write open brackets. Similarly, for the open ball and closed ball. So, in a metric space, every closed sphere is a closed set. Now, next we have intersection of family of closed sets in a metric space is closed. Suppose Ci is the family of closed sets. Then we know that intersection of Ci, I is in the suffix, I belonging to I is not equal to 5. Means it is non-empty, since the empty set is closed by definition. Thus we can assume each Ci to be non-empty. Let Cn be the sequence in intersection of Ci where I belongs to I, and this sequence converges to some x belonging to x. For each I belonging to I, we have the sequence Cn is contained in some Ci. So it means x belongs to Ci, because we are given that this Ci is closed. So it means x belongs to Ci for each I belonging to I, because we are given that Ci is a family of closed subsets. So it means C1, C2, C3, which are members of this family, these are closed. If the members are closed, it means it contains its limit point. because the sequence converges to X. So it means X belongs to Ci for each I because Ci is closed. If X belongs to Ci for each I, it means X belongs to intersection of Ci for I belonging to I. So it means the limit point belong to this intersection. It means intersection of family of closed sets in a matrix space is closed. Now one more theorem. We will show that any finite union of closed subsets of a matrix space X is also closed, but arbitrary union of closed subsets of X need not be closed. So first of all, we will show that finite union of closed subsets of a matrix space X is closed. For this, we will consider a finite closed subsets of a matrix space. Suppose C1, C2, Cn are closed subsets of a matrix space X. Let at least one of C1, C2, Cn be non-empty. So it means the union is non-empty. Let Cn be a sequence in C1 union C2 union Cn that converges to some X belonging to X. Now we want to show that this union is closed. It means we want to show that this X is in this union, because if X belongs to limit point X belongs to this union, it means this union is closed. We know that a sequence has infinitely many terms. So one of these C1, C2, Cn contains infinitely many terms of the sequence. It means subsequence of Cn lies entirely inside Cj. Since each subsequence of a convergent sequence also converges with the same limit, and we are given that Cj is closed, it means X belongs to Cj. But where is this Cj? Cj is a member of the family. It means Cj is contained in the union of these Ci's, means C1 union C2 union Cn. Hence, finite union of closed subsets of the matrix space X is also closed. Now we have proved the first part of the theorem. Now for the second part, we have to prove that arbitrary union of closed subsets of X need not be closed. So here we have used the word finite. Means finite union of closed subsets of a matrix space X is closed. So the word finite is essential here, because if the union is not finite, then the union is not of finite closed subset, then it may not be closed. For example, in the real line R, we can write the open interval 0 to 1 as union of n belonging to we can write 0 1 as union of n greater than or equal to 1 union of closed interval 1 upon n to 1 minus 1 upon n, where n is greater than or equal to 1. Clearly, as n tends to infinity, 1 upon n tends to 0, and 1 minus 1 upon n tends to 1 as n tends to infinity. So we can write open interval 0 as union of closed interval 1 upon n to 1 minus 1 upon n, where n is greater than or equal to 1. And this 0 1 is not closed subset of R. It means arbitrary union of closed subsets need not be closed because it is open here. Similarly, we consider one more example. If Fn is a sequence of closed interval 1 upon n to 1 on the real line, then their union of n equal to 1 to infinity Fn, it should be actually together, is the set 0 to 1. It is open at 0 and closed at 1, because as 1 upon n tends to 0 as n tends to infinity. So it is open at 0 and closed at 1. Again, this is not a closed subset of the real line because it is semi-closed, or we can say it is semi-open. So the word finite is essential, and it is false that union of infinitely many closed subsets has to be closed. It may be closed, it may not be closed. So arbitrary union of closed subsets of X need not be closed. Now the interior of a set. Let S be a subset of X and Xt be a metric space. Then we say that X belongs to S is an interior point of S if there exists R greater than 0 such that we have an open ball centered at X and radius R which belongs to S. The set of interior point is denoted by interior of A, or we should have S here, interior of S, or we write dot here means 0 S naught. So the interior of for interior of a set we should have a real number R greater than 0 such that open ball centered at X belonging to X and radius R belongs to the set. And for example, we see in this figure, this is the set S. This is the set S. Clearly, P is inside the set. It means P belongs to interior of S. But Q does not belong to interior of S. If we consider this set where X is greater than 0 and Y is greater than 0, we see that A is in the interior of S and B and C does not belong to interior of S. B is on the boundary and C is on the boundary. B and C does not belong to interior of S. So we say that X is an interior point of S if there exists R greater than 0 such that ball centered at X and radius R belongs to the set. And for exterior of a set, the exterior of the exterior is the interior of the complement of the set. It means exterior of S is the interior of S complement. It means a point is exterior point if and only if open ball around it is entirely outside the set. It means it contains no point of the set. Here Q is the exterior of a set S. Q is in the exterior of the set S. And X belongs to exterior of A if and only if there exists R greater than 0 such that a ball centered at X and radius R is a subset of X minus S, means complement of S. Now boundary point. A point X belonging to X is called a boundary point of S if every small ball centered at X has non-empty intersection with both S and its complement. It means X is a boundary point if and only for all R greater than 0 there exists X and Y belonging to BXR, means ball centered at X and radius R if X belongs to S and Y belongs to complement of S. The set of boundary points is its boundary, and we denote the boundary by this notation or this notation. Now frontier point. A point X is called the frontier point of A if it is a limit point of both the set A and its complement. It is neither exterior point nor the interior point. The set of all the frontier point is denoted like this. The frontier is not to be confused with the boundary, as we have seen in some books, even though they are sometimes equal. If the frontier points are in the set also, then it is a boundary point. If the frontier point does not belong to the set, then it is not a boundary point, then we will write it only frontier point. Suppose we are given a closed interval AB. Then how will we calculate its interior, exterior and frontier with respect to the usual metric? So to calculate the Interior of A is the interior of A which is closed interval 0 when is 0 1, and we know that its exterior is the complement part, so it is minus infinity to 0 union 1 to infinity, and frontier is the set 0 to 1. This can be calculated easily using the definitions which we have discussed in last slide. Now last definition is Hausdorff metric. If we are given two distinct points x and y, these are distinct points, then there exists r greater than 0 such that intersection of ball centered at x and radius r and ball centered at y and radius r is empty set. So this is the definition of Hausdorff metric. Now one more theorem. In a metric space, the complement of a finite set is open. If we take complement of any finite set, it is always open. Let Xt be a metric space and S is a subset of X which is finite. Now we will prove that S dash is open. Complement of a finite set. S is finite set, its complement S dash is open. So to prove S dash is open, we can prove that S is closed, because we know that complement of open set is closed. Let S has n elements for some n belonging to n. N is a set of natural numbers, and we write S equal to x1, x2, xn. Suppose we consider a singleton set xj, where j may be any one of 1, 2, 3 up to n. The complement of xj is s minus xj. Let y belongs to x minus xj. It means there exists a distance of xj from y is greater than 0. dxjy is greater than 0. dxjy is the distance of y and xj with respect to metric d. Suppose this we denote by r. R is equal to distance of xj from y divided by 2, means half of the distance of xj from y. Then the ball centered at y with radius r, which is nothing but byr, which we denote like this, is the set of all the points z belonging to x such that distance of z from y is less than r, and r we have taken to be dxj upon 2, and this ball is contained in x minus xj, because y belongs to x minus xj. Hence y belongs to interior of s minus xj. By the definition of interior point, it means x minus xj is an open set. So the singleton set xj is closed. Because x minus xj is open set, we note complement of a open set is closed. So it means singleton xj is closed for j equal to 1 belonging to 1, 2, 3 up to n. It means s is equal to j equal to 1 to n xj. S is a union of these xj's, because s is nothing but x1, x2, xn, and we have proved that xj is closed. So s is finite union of closed sets, hence s is closed. So we have proved that S dash is open, means complement of finite set is open. Thank you.